Welcome to today's deep dive. We have a truly fascinating stack of material to go through with you today, all centered on a mathematical framework known as algebraic structures.
Yes, it is a very rich topic.
For those of you who regularly explore the architecture of reality, whether you're working in computer science, physics, or just possess an insatiable curiosity about how things actually work, you probably already know that mathematics is the underlying language of the universe.
Absolutely.
But our mission today is to provide some professional commentary on a very specific, somewhat hidden dialect of that language. We're talking about group theory,
Right.
and we're going to bypass the rote memorization and, just dive straight into the engine room. We'll be looking at the structural definitions of groups, exploring geometric symmetries, and most importantly, dissecting how these theoretical concepts are the literal bedrock for everything from the cryptographic security of your digital life to the fundamental uncertainty of quantum mechanics.
It is great to be here with you. And by the end of this deep dive, the goal is for you to recognize these patterns of symmetry, not just as abstract algebra, but as the actual governing dynamics of the physical and digital world around you.
Yeah?
Because these concepts, they define the rigid boundaries of what is mathematically possible. We are going to explore the context, connect the dots, and really look at the actual mechanisms making modern technology function.
Okay, let's unpack this. Before we can talk about securing global communication networks or, subatomic particle physics, we have to define the boundaries.
We do.
To even qualify as a group in a mathematical sense, a set of elements combined with a specific operation like addition or multiplication has to flawlessly satisfy a strict constitution of four laws. It's essentially an ecosystem with absolute rules.
Exactly. It's a very rigid ecosystem. The first law is closure.
Okay.
If you take any two elements in your defined set and apply your operation, the result must be another element that already exists within the exact same set. You can never, mathematically speaking, escape the boundaries of the group.
So if I'm operating within a specific group, closure basically guarantees that no combination of valid moves will suddenly generate an invalid output or throw an error. I am permanently contained within that defined space.
Perfectly stated. You are locked in. The second rule is the associative law.
Right.
This simply dictates that the grouping of the elements doesn't change the outcome. If you are combining A, B, and C, processing A and B first, then C yields the exact same state as processing B and C first, then A. The sequence of grouping is flexible.
Right, which makes complex calculations a lot more manageable. So we have closure and associativity.
Ugh.
But a system needs stability, which leads us to the third requirement.
Yes, the identity element.
Right.
There must be an element that effectively acts as a neutral state. If we're talking about addition, it's zero. Adding zero leaves you exactly where you started.
Yes, the sort of do-nothing state.
Exactly. And that naturally leads to the fourth and final requirement, the inverse element.
The undo button.
That's a great way to put it. For every single action you take in this ecosystem, there must be a mathematically guaranteed undo button. Combining an element with its specific inverse will always return you to that neutral identity element. If you step forward, you can step back.
Okay, so that makes a full group.
Right. A simpler structure, like a semigroup, well, that only requires closure and associativity. It's the addition of the identity and inverse properties that locks the structure into a full-fledged group.
I follow the logic perfectly.
Yeah.
But looking at these four pillars, closure, associativity, identity, inverses, there's a glaring omission for anyone who remembers their foundational high school algebra.
You're thinking of commutativity.
Yes, commutativity. The law that says A combined with B is identical to B combined with A. 3 plus 4 equals 4 plus 3. Why isn't the ability to swap the order of elements a fundamental requirement for a group?
What's really fascinating here is that commutativity is completely absent from the core definition because it is actually a rare, highly specialized property. Yes, it is by no means a guarantee in nature or in higher math. If a group does possess this fifth property, where the order of operations is entirely irrelevant, it earns a special classification. It's called an abelian group.
Abelian.
Right. Named after the 19th century Norwegian mathematician Henrik Abel, who did some groundbreaking work in this area before tragically passing away at just 26.
Wow, 26. So abelian just means commutative, meaning A times B equals B times A.
Correct. But if a group lacks this property, if A combined with B yields a fundamentally different reality than B combined with A, it is a non-abelian or non-commutative group.
Order matters.
Exactly. In those systems, the strict sequence of events fundamentally alters the final state of the system.
To make this tangible for everyone listening, let's look at the geometry of an equilateral triangle. Mathematically, the symmetries of this triangle form a group known as the permutation group S3, and this perfectly illustrates why order matters.
Geometric symmetry is the absolute best way to visualize non-abelian groups. S3 represents the exact set of physical manipulations you can apply to an equilateral triangle, so that, when you place it back down, its footprint is indistinguishable from its starting position.
It looks exactly the same.
Right, and there are exactly 6 valid moves in this group. First, 3 rotations, 0 degrees, which is our identity element, then 120 degrees, and 240 degrees.
Okay.
Next, 3 reflections. Because the triangle has 3 lines of symmetry, you can flip it across any of those 3 axes.
And these 6 physical moves form a valid group because they satisfy the 4 laws. Any 2 moves combined, like, say, a flip and then a rotation, results into position equivalent to one of the other standard moves.
Yes.
That's closure. And the 0-degree rotation acts as the identity, and flipping the triangle twice on the exact same axis acts as the inverse, bringing you back to neutral.
Exactly. It's a perfect group. But the crucial insight is what happens when you alter the sequence.
The non-commutative part.
Right. If you flip the triangle across its vertical axis and then rotate it 120 degrees clockwise, vertex A might end up on the bottom right.
Okay.
But if you rotate it 120 degrees clockwise first and then apply the exact same vertical flip, vertex A ends up on the bottom left.
The final state is physically different.
It is. The order dictates reality. Therefore, the S3 symmetry group is strictly non-abelian.
Here's where it gets really interesting, because the math governing how we flip a piece of cardboard on a desk is the exact same math governing subatomic physics.
Yes, it is.
We can draw a direct line from the non-abelian nature of that triangle to the very foundations of quantum mechanics.
If we connect this to the bigger picture, it fundamentally changes how we view the universe. In classical physics, properties commute. But in quantum mechanics, physical observables, a particle's position, its momentum, its angular momentum, they are represented by mathematical matrices called operators. And a defining feature of our universe is that many of these quantum operators form non-abelian groups. Applying them in a different sequence yields a completely different physical measurement.
So measuring position and then momentum gives a different result than measuring momentum and then position.
Exactly. And this mathematical structure is the literal, undeniable foundation for the Heisenberg uncertainty principle.
Wow.
The reason you cannot measure a particle's position and momentum simultaneously with absolute precision isn't simply because our microscopes aren't powerful enough. It is because the mathematical operators for position and momentum do not commute.
The framework of reality itself just does not allow it.
Exactly. A times B simply does not equal B times A at the subatomic level. Furthermore, manipulating these complex, non-commutative group structures is exactly how engineers are currently building quantum computers. They are designing algorithms that exploit these sequential dependencies.
It's incredible to think that the rigid rules of abstract algebra dictate the fuzziness of the quantum world.
It really is.
But stepping away from the subatomic, let's look at the sheer scale of these groups. Up to this point, we've discussed finite sets, like the 6 moves of a triangle. But many foundational groups are infinite.
Oh, definitely. Infinite groups are usually what we encounter first in mathematics. The continuous set of all real numbers under addition is an infinite abelian group.
Because it just keeps going.
Right. It stretches forever, flawlessly obeying the 4 laws. You also have Lie groups, which are continuous infinite groups used to model smooth transformations. For instance, the Lie group SO3 represents all possible continuous rotations of an object in 3-dimensional space.
Meaning there are infinite tiny adjustments.
Exactly. There isn't a set number of clicks you can rotate a sphere. The group elements are infinitely dense.
Right. But while infinite groups describe continuous physical space, the digital universe, the architecture powering the device you're listening to this on right now, requires absolute discrete boundaries. It relies entirely on finite groups, specifically utilizing modular arithmetic.
Modular arithmetic is essentially wrapping around. Instead of a number line that stretches infinitely into the distance, imagine a number line wrapped around a circle.
Okay.
When you reach the maximum value, you don't keep going. You snap back to 0. The classic analogy is a 12-hour clock face.
Right. If it's 10 o'clock and you add 4 hours, it's 2 o'clock.
Exactly. You wrap around, But the true power of this finite structure emerges when we restrict the boundary even further.
Specifically modulo 2, binary logic.
Precisely. A finite group consisting of only two elements, 0 and 1. Modulo 2 arithmetic is the heartbeat of digital architecture.
Because it's on or off.
Right. Every logical gate in a microchip, every packet of data routing through the internet is governed by the strict finite group laws of modulo 2. It forces infinite streams of information into manageable, predictable loops that a processor can mathematically guarantee.
And within these finite structures, there's a specific mechanism that makes computation incredibly efficient, the cyclic group. This is where you can generate an entire universe of elements from just one single seed. How exactly does a cyclic group function?
The cyclic group is a group that can be completely generated by taking the successive powers of a single foundational element.
The generator.
Right. If you take this generator element and raise it to the power of 1, then the power of 2, then 3, and so on, it will methodically cycle through and produce every single valid element in the entire group.
Until it loops back.
Exactly, before eventually hitting the identity element and starting the loop all over again.
To visualize this, let's look at complex numbers. Before we get into the algebra, imagine that standard circle graph on a plane. The cyclic group concept maps perfectly onto something called the nth roots of unity.
It's a beautiful geometric visualization. In complex mathematics, the nth roots of unity are a specific set of numbers that, when raised to the power of n, equal exactly 1.
Okay.
If we look at the fourth roots of unity, we are looking for 4 specific numbers that complete this cycle. Those elements are 1, the imaginary number I, -1, and -I.
And if we use I as our generator element, we can spin up the whole group.
Exactly. I to the first power is I squared is -1, I to the third is -I, and I to the fourth power brings you right back to 1, the identity element.
It cycles perfectly.
It does, and if you plot these 4 points on the complex plane, they sit perfectly on the unit circle at 90-degree intervals. They map identically to the 4 rotational symmetries of a physical square. The algebraic cycling and the geometric rotation are mathematically identical.
So what does this all mean when we start dissecting these structures? We have these massive systems, but they aren't monolithic. They contain subgroups, which essentially function like Russian nesting dolls.
A subgroup is a smaller, self-contained subset of elements living inside a parent group.
Okay.
The critical detail is that this smaller subset must independently satisfy all 4 group laws using the exact same operation as the parent. It is a fully functional, mathematically sound ecosystem tucked inside a larger one.
So looking at our infinite groups, the integers, positive and negative whole numbers, they form a perfect subgroup inside the vast, continuous group of real numbers.
Yes, and the real numbers form a subgroup inside the complex numbers. But you can also create highly specific subgroups using that generator trick we just discussed.
Right.
If you are operating within the multiplicative group of real numbers and you take the number 2, you can generate an infinite subgroup just by looking at its powers.
So 1/4, 1/2, 1, 2, 4, 8.
Exactly. If you multiply any 2 numbers in that specific subset, the answer is always another number in that subset. It has closure, it has the identity of 1, and every element has an inverse. It is mathematically autonomous.
And you find these tucked inside finite groups as well. If we look back at the fourth roots of unity 1, I, -1, -I, there's a tiny subgroup hiding in there.
Yes, there is.
Just the elements 1 and -1. 1 times 1 is 1. -1 times -1 is 1. It ignores the complex elements entirely, but still perfectly obeys the constitution of the group.
Exactly. Identifying these subgroups allows mathematicians and computer scientists to isolate behaviors, simplify massive calculations, and find structural weaknesses or efficiencies in complex systems.
Which brings us to the ultimate payoff of this entire conversation. We've explored the abstract rules, the geometric symmetries of non-abelian groups, infinite spaces, and finite cyclic loops. How do these exact mechanisms actually build and protect the modern digital ecosystem?
Well, if we connect this to the bigger picture, without group theory, modern technology just collapses. Let's start with digital signal processing, or DSP.
Okay.
When your phone streams a high-definition video or processes a voice call in real time, it has to instantly analyze massive, chaotic waves of continuous data. It does this using the fast Fourier transform, or FFT algorithm.
And the FFT doesn't just crunch the raw numbers sequentially, does it? It exploits the symmetries of the group.
Precisely. The core engine of the FFT algorithm is built entirely on the cyclic nth roots of unity we just discussed.
The circle we talked about.
Right. Because those roots form a finite repeating loop around a circle, the algorithm can essentially fold the continuous audio wave in on itself. By
Wow.
utilizing the symmetry of the subgroups within those complex roots, the FFT drastically reduces the number of multiplications the processor has to perform. It turns a computational nightmare into an elegant, instantly solvable cycle. High-speed DSP is purely an application of cyclic group theory.
That is wild.
Yeah.
But processing the data is only half the battle. When data is transmitted wirelessly, it encounters interference and noise. Bits flip, zeros become ones. How do we ensure a corrupted text message or photo still arrives perfectly intact? This relies on error-correcting codes.
And error-correcting codes rely heavily on permutation groups, very similar to the S3 group we use for the triangle.
Right.
Information is encoded using what are known as cyclic codes. Engineers use specific mathematical structures, like automorphism groups, which define the strict symmetries of valid data sequences. Because the data is encoded as a cyclic group, you can perform a cyclic shift, moving the bits along the chain, and the sequence remains a structurally valid code word.
So if a bit gets flipped by background radiation or signal noise, the system doesn't just, guess what went wrong?
No, it uses mathematics. When a corrupted sequence arrives, it fundamentally violates the closure law of that specific group. The algorithm instantly detects this mathematically invalid state.
It knows you left the group.
Exactly. Then, using permutation decoding, it utilizes the strict symmetries of the group to systematically isolate the errors, shifting them into dedicated parity check sectors of the data block.
And then it fixes them.
Yes. Once isolated, it applies the mathematical inverse element to flip the bits back to their correct state. It leverages group symmetry to perfectly rebuild shattered information.
Okay, so group theory optimizes our media, and its symmetries mathematically heal our corrupted data. But the most critical application in the modern era has to be keeping that data secure. Cryptography.
Without question. The cryptographic protocols that secure global banking, secure web browsing, and your private communications are fundamentally powered by the rigidity of modular arithmetic and group operations. Take the discrete logarithm problem,
Okay.
which is the foundation for the Diffie-Hellman key exchange.
Explain the insight behind that. Why is a discrete logarithm so hard for a computer to crack? Because in standard algebra, logarithms are fairly easy to calculate.
In standard continuous algebra, logarithms have a predictable trend. If the input gets bigger, the output gets bigger. You can hone in on the answer.
They could follow the curve.
Right. But when you place a logarithm inside a finite cyclic group using modular wraparound arithmetic, you destroy that predictable trend.
Because of the clock math.
Exactly. Taking a generator element and raising it to a massive power in a finite modular field is computationally easy for the computer to do. But because the numbers wrap around the circle thousands of times, the final output looks like completely random noise.
So it's a mathematical trapdoor.
Exactly. Given the final result and knowing the original generator, an attacker cannot reverse the process to find the specific exponent or the key that was used. They can't follow a trend. They would have to brute force guess every single cycle, which is mathematically unfeasible for even the most powerful supercomputers.
Wow.
The structure of the finite group creates an unbreakable one-way function.
This exact principle of using group structures to create trapdoors is also what powers RSA encryption, which relies on the difficulty of factoring massive primes within a modular system.
Yes.
But I want to touch on elliptic curve cryptography, or ECC, because it's what secures almost every modern smartphone. How does ECC utilize group laws differently?
ECC is arguably the most elegant application of group theory in cryptography. Instead of just using raw numbers, ECC defines its group elements as geometric points sitting on a specific mathematical curve over a finite field.
Okay, geometry again?
Right. The operation for this group involves drawing a tangent line through 2 points on the curve, finding where it intersects the curve a third time, and then reflecting it.
And because it's mathematically defined as a group, this geometric gymnastics still flawlessly obeys closure, associativity, and has specific identity and inverse elements.
Perfectly. But because the group operation involves complex geometric reflections wrapping around a finite modular field, the resulting trapdoor is astronomically more complex to reverse than traditional RSA math.
Which means you can achieve the exact same level of impenetrable security using a significantly smaller cryptographic key.
Exactly, and that smaller key size requires vastly less computational overhead. It is the sole mathematical reason your smartphone can secure highly encrypted data locally without instantly draining its battery. ECC uses advanced geometric group structures to optimize security for mobile hardware.
It's astounding. Let's briefly retrace the path we've taken today.
Sure.
We started by defining the absolute laws of an algebraic ecosystem: closure, associativity, identity, and inverses. We visualized how the strict order of operations in non-abelian geometric groups, like the symmetries of a triangle, perfectly maps to the non-commutative operators that dictate quantum uncertainty. We explored how continuous infinite groups model our physical space, while finite modular loops provide the boundaries for binary logic. Finally, we uncovered how the repeating symmetries of cyclic groups and subgroups mathematically process our audio, recover our corrupted data, and provide the cryptographic trapdoors that secure the global digital economy.
It is a phenomenal progression from abstract logic to the very infrastructure of society. And this raises an important question, a final thought I want you to consider as we wrap up today.
Okay, let's hear it.
If the strict laws of group theory and geometric symmetry flawlessly dictate the transmission and encryption of a simple text message on your device, while simultaneously governing the fundamental non-commutative limits of subatomic particles, does that suggest that the physical universe itself isn't actually made of solid matter at its deepest core? Is reality ultimately just one massive, intricately interconnected geometric group simply waiting for us to fully decode its symmetries?
That is a profound perspective, and definitely something that's going to occupy my mind for a while. To you, listening right now, I highly encourage you to look closely at your world today. Look for the hidden clock math, look for the symmetries, and realize there is an incredibly elegant set of mathematical rules quietly holding it all together. Thank you so much for taking this deep dive with us. We'll catch you next time.